Hi, we'll talk about friend recommendations, particularly retrieval of friend recommendations. So, in social networks, you have um, connections that users make organically, and it helps them if you are able to recommend good connections or friends for them to make. There's research from LinkedIn which indicates that if users are able to graduate to a certain level of the network size, then it aids future opportunities in contact LinkedIn. It is about job opportunities. But then I think it's not far stretched to understand that a certain network size will help derive more from the social network. So yeah, with that context, today we'll look at some approaches for friend recommendation retrieval. We'll start with some baselines, and then we'll move on to more state of the art. Okay, so I was talking to an 11-year-old, my daughter, about how you would approach this problem, and her her first response was, "That's so easy. You just recommend me friends of friends." And it's not, that's not actually too far away from the state of the art. Um, at least what was the state of the art a few years ago. So I've shown an image here, which is, imagine C is the viewer, the person who's on your app right now, and you're trying to recommend friends to them. Then what you could do is you could look at their first degree nodes, which are A and E, and then you could look at the second degree from there. So B, D, F, G, and J, right? Um, so that will be friends of friends. And in addition, you can try to see how many paths lead to each candidate here. So for instance, B, there are two paths leading of length 2 from C, but J, there's only a single path. So one approach is, let's just call it mutual friend count. One approach is to find all options with at least one mutual friend, and then between these options, choose the ones which have more number of mutual friends, right? And now what remains is at an industrial scale recommender system with potentially, billions of users, accounts might be actually, in tens of billions. Um, how do you run this in scale with the capacity and latency that makes sense for you for the application in the context of your business? And towards that, there's some research. Um, I've linked to one from Facebook about how to do this. So this is kind of the baseline here, which is already an awesome baseline, like running friends of friends at scale. In this video, we'll focus more on the quality and less on the scalability, which is a huge and interesting topic by itself. Okay, so the quality of the recommendation. Okay, now one definition of what is success when you're doing this, I'm going to borrow, and one of the papers I'll refer to is Snap's. Snap had this paper, embedding based retrieval. We're not going to do much here, but I just want to make a minor digression into how do you, when you're coming up with an improvement, so-called improvement of uh, friend recommendation retrieval, how do you know it's actually improving? What is the metric you can use for to see in your experiments if you're improving retrieval? And the reason it's important is because retrieval is at the bottom of the stack. Actually, they have a very nice diagram of to recommend friends, you have potentially billions of candidates, and you find through retrieval, you find maybe a set of candidates that you further rank. Now, so retrieval's job is to come up with this set. In this case, they've used 10,000, but depends on your application and resources, what this funnel size is. So, so the metric they recommend and I endorse is the goal of the retrieval phase is to include as many potential friends as possible to the next phase. And recall is used to measure its effectiveness. What recall is a general metric you'll find in retrieval, not just in friend retrieval, but in all retrievals. So for instance, um, like let's say you're building a video recommender, and so people might be searching videos and watching them, or you have a recommender system that does it. That recall applies there as well. Recall is defined as the number of candidates, in this case it's friends. Let's stay in the friends space. The number of friends that were made by the viewer in this case that were in the retrieved set. So in this set that is retrieved, 10,000 here, you see how many of these 10,000 were actually friends made by the user, either through your recommender system or separately by them searching or chancing them on some page or organically friending, right? So it could be any way. So the number of friends made that were in the retrieve set divided by all the friends made. Okay, so recall is a general definition of what is success. The reason I'm taking this digression is because now onwards we will talk about potential ways to improve this friends of friends. And so the notion of when you define improve, it's good to have a metric which helps you codify or see if you're on the right track. Yeah. Okay. So first we talked about making this graph of users and edges being current friendship relationship that has been established, and then we talked about two length graph walks starting with the user, the viewer, and sort of ranking them based on um, or based on maximum number of paths that lead to the candidate. Okay. Now, one could claim that not all um, first degree nodes are of equal importance. For instance, E in this case has 5 friends. A has 3 friends. One of the approaches that was used by Kip et al. In 2017, graph convolutional neural networks, is to use 1 by square root degree. You can apply the same. You can kind of say that, the weight of the path CAB is is higher than the weight of the path CEB because E has more edges coming out of it. So, and pathologically, for instance, A could have the 3 edges and E could have 3,000 edges. This um, this could be quite a large difference. And then this difference, you suppose you do 1 by square root degree, that ratio between the two will be much more, and it'll show up in your ranking differences. So there's a lot of theoretical foundation of this. You can read the 2017 paper by Kip et al. Linked here. The broad idea is can we find which parts are, are encode the friend relationship better? And what are the features? The features we have are, we talked about the number of friends of this first degree friend, right? Number of paths going out of this node. Maybe you could look at how recently the relationship between C and this first degree was set up, the viewer and this first degree was set up. For instance, maybe CA relationship was set up a year ago, but CE friendship was just created. That stands to reason that the out degree from E, the second hop, so to speak, from E, that has been relatively less explored, and it might be better for you to for the recommender system to up rank these candidates right now. Yeah, so recency of the edge between the viewer and the first hop, that could help. Maybe there are other attributes, for instance, maybe geographical location. That's one of the things that also the SNAP paper talks about, maybe geographical location. So yeah, I mean, in general, the literature of graph walks, this is generally called graph walks. Literature of graph walks has explored the idea of sampling the next node in a walk based on edge features and node features. So that brings us to Deepwalk and Node2Vec. Deepwalk, seminal paper, you can Brian Perosi et al. You can read that. I encourage you to read that. What they do is they try to find embeddings of nodes, but the way they train the embeddings is by doing these random walks, and these random walks are start from the viewer and they end at a certain spot, and these starting and ending are become their inputs to how they find embeddings. Okay, at a very high level, it is actually a very direct translation of what we were just talking about. If we could, instead of just deterministically finding these second degrees, right, based on these graph walks, you could challenge yourself to say that, hey, I'm going to sample these and create a training data set that which sort of says CB twice, because there are two walks here, and CD and CF and CG and CJ once, and ask your embedding based approach to learn that, to find embeddings that actually do make embeddings of C and B, J, G, D, and F closer, right? So that's the embedding based approach. There's this, so Deepwalk uses random walks on the graph to generate training samples, and Node2Vec extends it by enabling biased sampling. Okay. Now, so far we have been talking about graph search. In a general friend graph, you can expect a lot of clusters. So let's view this in the form of clusters. So imagine C has, let's just say 30 friends, okay, on this social network. Now, stands to reason that there are like distinct sort of social circles, social clusters that these 30 friends are from. And that's the idea. That can you take the social graph and find these clusters? Of course, there are some overlaps. You'll have see having some friends that are in multiple social clusters, but I think this language here says it well. clusters are formed based on dense areas of the graph, often revealing latent communities. Nodes with many paths ending on them, but without direct connections, are likely in the same cluster as the source node. So we are defining cluster as like a lot of edges between them. And then we are saying inside a cluster, if there are nodes that do not have an edge between them, which means they are not currently friends, then they could be good recommendations. Okay, so you identify these social circles, and then if people are not connected, that could be good recommendations. Now, the problem with clustering is it's computationally complex, especially at multiple billion number of accounts, number of users in your social graph. Um, it could take a lot of time. Also, like with you know, does that mean you will be running your clustering every month, every week, every day, every 5 minutes? It's hard to um, like find like run these large experiments and find the right trade-off and then implement it at the capacity profile that you're looking for if you're just purely doing clustering. But this idea of social clusters we will retain. In fact, that was built upon by 2024, a very recent paper from Snap. We will very briefly cover. Okay. Right. So far what we discussed was graph walks, friends of friends, great approach. And then you could augment it by saying, hey, some paths, some walks in your graph are actually more important because you have found that some features of the edge or some features of the node work well in your A/B tests in your experiments. And then we talked about how to step into embedding-based retrieval by taking the source and destination of these graph walks as as training data, and then learning embeddings from it. And then we talked about clusters, where we are trying to take the social graph and find, and we're trying to find social clusters from it. One deep but very important topic is this one where if you were to expose your tests either to everyone in a social cluster or no one, you are more likely to learn accurately estimate the impact of your test when it is exposed to the entire population. So it's called network effect, or network interference bias. Essentially, what it says is that if they're in a closed-net cluster, if you are only introducing normally in a test, what happens, you just sample a few users and you introduce a change. And that's great for like things like content recommendation, individual decisions. But in a social network, you're not able to properly measure the impact of a change if you just sample that way. It's a deep topic. I don't want to step into it and do a bad job of explaining it, but I'm just trying to say that clustering could help could help you in so that your experiment is exposed to the entire cluster or not. Okay. Yeah, two-tower models. We'll continue with the embedding thread that we started in the Deepwalk and Node2Vec idea, but here we'll take some of the advances that are sort of the cutting edge in content recommendations. So broadly what we're going to do is there's a viewer tower and a candidate tower, and we are going to learn how to take all the features on the viewer side, the ID of the feature that allows you to essentially learn a large a vector, a floating point vector, which sort of explains everything unique to the user. It's similar to how LLMs learn about tokens. So here you're trying to do it based on the viewer. So the viewer ID, maybe the features of the viewer, maybe past searches of the viewer. On the candidate side, similarly, you can use names. It will help you match with the searches. You can take the candidate features. You can take the candidate ID. You can, in features, I've just written features, but essentially in these features, both on the viewer and candidate side, you can look at their graph, their first degree nodes, like their current friends. If you have the capacity to, you can even sample some of their second degree. But even staying within first degree is very powerful. If you maintain the sequence of friends made by the viewer and the sequence of friends made by the candidate, that allows you to use transformer models to also learn based on recency. Like if recency is important in your application, then your sequence modeling of the viewer friend making history feature input will allow you to learn recency biased transformation of your friends. So basically, this we try to learn an embedding of the viewer and all the candidates, and this model is trained from real data. So every time a viewer actually makes a friend on the network through your recommendation system or even throughout. So every aspect of the ground truth you can take as a positive example and say that, this viewer made a friend on this network with this candidate. So I need to learn an embedding of this viewer, embedding of the candidate that has high dot product or that is close. That's the idea of embedding based retrieval. There are a lot of references you can and sample code that you can see. Now, once you have trained that, then you use it in nearest neighbor search and real-time systems. The benefit of nearest neighbor search in practice, at billion scale as well, they are much faster than graph walks, and the capacity profile is also much better. If you're able to make this work, there are a lot of pros and there are a lot of pros of this approach, but I wouldn't compare them. I think again, one of the things that I'll go back to is that is in the Snap 2023 paper, they say that embedding-based retrieval complements traditional friend of friends or traditional graph-based sources. It's not a competition. They are both good. They both complement each other. And if you look at just the results, I think that they say that embedding-based retrieval for Snap was increased the friendships made from friend recommendations, that's their service, by adding embedding-based retrieval, friendships from this service increased by 5 to 10%. This is a higher impact in markets where there is already high user growth. The overlap, this is the part I wanted to stress on, the overlap between the top suggestions of embedding-based retrieval and friend of friends, which is the graph search one, right? So the overlap between embedding-based and graph-based is very low in their context. That's what they found, which is good, right? Because that means these two sources of retrieval are complementary, they are additive. And they also find that the efficiency of candidates coming from embedding-based retrieval is high, because the impression to friend request and friend request to reciprocation, which means acceptance. So both of these are on par with candidates from friend of friends in this 2023 paper. Okay. So coming back, embedding-based retrieval has a bunch of you know salient features or graph search, but the way in which I recommend using it is additive in addition to graph search. And as we saw in the SNAP paper, at least in SNAP, they found it to add 5 to 10% of friendships made through friend recommendation service. B, the overlap between the candidates of graph search and embedding-based retrieval is very low. And sorry, the third point was, yeah, and the efficiency. Sorry, the efficiency of candidates coming from embedding-based retrieval is on par with candidates coming from graph search, because the impression to friend request and friend request to acceptance were both at par. Okay. Right. So two towers, we talked about it. It's a way of learning and embedding of the viewer and embedding of the candidate, and finding the top candidates by nearest neighbor search. Um, Here I talk about a little how to just prime it with the data before the start of your training data, because people might have been making friends on your platform for years, but you'll miss that in your training data, right? And and we talk about in this article we talk about some of the hardest parts of embedding based retrieval, like what is called embedding collapse, which means that you're not able to you're learning embeddings in a way that is not truly using the number of dimensions it has. It is not able to recognize the uniqueness of all users. It is focusing too much on the power users. So let me, there's a lot here to cover, but let me quickly go back to um, actually a follow-up of the SNAP 2023 paper and the 2024 paper, where they find an additional 11% improvement in friends made with communication. Now, let's first look at the metric. It's very important. Um, often in your recommender system, you're making a friend on the platform is just the starting point. After that, you expect users to communicate or engage in content from each other, or um, derive value from that social relationship, right? And let's call it downstream value from that relationship. So in this paper they use that as a metric, and they find that they do a few more changes, and we'll go into that. And they find that with their changes, they find 11% more improvement in friends made with communication, which is the downstream value. All right. So I'm stressing this point because in your service, in your social network, when you are recommending friends, you'll want to understand, uh, through data analysis, you want to understand what downstream value after that friend relationship leads to lasting value for the users. Like what leads to retention? Like our users on your social network, after they make the relationship, what sort of actions do they do with each other that makes them find unique value of your application? And you'll want to measure that um, as to which of these friends relationship recommendations that you're suggesting are leading to friend relationships being set up, which are leading to this downstream value. And why? Because that will be leading to your final retention. Right? Once you have established that causality, and you trace it all the way back to your recall metric, that gives your training, the model training, a clean path to optimizing your eventual business goal. Okay, so a very brief summary of the 2024 paper by the Snap Retrieval team, where what they say is that, if you go back to this idea of clusters, right? We talked, I think here, clustering. We said that users are in multiple social graphs, and then they say that trying to learn the same embedding of a viewer is possible. I think the Pinner Farmer paper did achieve that, even in the case of content recommendations. But also, you could say that users are multimodal, and it's very hard to learn all the interests of the user. But in the case of friend recommendations, what they find is, how about we sample some of the friends of the user. Okay, in this case, this viewer, what I'm trying to show is that in this case, they have 6 friends on the platform, 1, 2, 3, 4, 5, 6. And let's assume the bold ones are the ones we sample. How we sample, they talk about a few methods in the paper, recency and how engaged they are in this relationship. So maybe viewer and friend 4, they chat all the time, but viewer and friend 2, they almost never do. So engagement, recency, maybe geography, etc. How to sample the first edge is a topic in itself. But after you sample some of the friends, they use the embeddings of the friends to find recommendations. So in the first paper, they learn a recommendation, learn an embedding of the user, and they search for that. And in the second paper, they learn an embedding of all users, but instead of searching with the embedding of the instead of searching with the embedding of the user, they sample some of the friends and they find the nearest neighbors of these samples. Specifically, they have 5 seeds. They call it 5 seeds. They sample 5 seeds and they search for them. And one thing that was interesting is they say that we also tested variants where we tried to explicitly include the searcher's embedding as part of the seed selection. So they say, it's natural to assume that, maybe also adding the embedding of the viewer could help. But they find that, interestingly, we did not find any notable difference whether or not we use the searcher embedding. We hypothesize that it is more important to do similarity search within each social circle, and excluding the searcher embedding may balance the results more evenly across searchers' social circles. So if you go back to this diagram, it is so maybe after sampling, they are more balanced between the user's social circle as opposed to adding the viewer. In the best case is it's kind of not helping, and you could say it even might hurt if it makes it more lopsided. Like, let's say 50% of the users are in one social circle. It stands reason the viewer will be closer to that social circle, and maybe in their context they found that adding the viewer embedding didn't help. You could make a case that it might help. If it's if there's a large social circle, then and adding the viewer does sample more from that. In some cases it might help, it might not. But I'm trying to show what is established research in this direction. Okay, so conclusion is we talked about graph search of friends. It's a great baseline. Doing it at scale is hard. and there are good papers for it. And we slowly saw the trajectory from graph search to clustering to graph search being used to collect training data that is used to find an embedding or latent representation. And then we talked about two-tower models and embedding-based retrieval directly. Right? Cool. If you're working in this area, and social networks or areas where users can derive value from each other, you're thinking about these questions. I hope you find them valuable. If not, please reach out to us. Yeah, thank you.